Hey everyone! If you're deep in study mode for the PPD or PDD exams, you know there are these certain concepts that just always seem to trip people up. Well, today we are going to tackle one of the biggest ones head-on: capillary breaks versus vapor barriers. We're going to get this so dialed in that you can walk into that exam feeling totally confident.
You know that feeling, right? You walk into a basement and you can just smell the dampness. Or you see paint bubbling up right at the base of a wall. That's our enemy, moisture. But here's the thing, and this is absolutely crucial. To fight it, you have to realize you're not fighting one enemy. You're fighting two, and they play by completely different rules.
So, on one side you've got liquid water. This is the visible enemy. It's the rain, the groundwater, the stuff you can actually see trying to get in. But then you've got this other thing, water vapor. And this is the invisible enemy. It's a gas, it's the humidity in the air, and it can move right through materials that look totally solid. Two very different problems need two very different solutions.
So here's our game plan for today. First, we're going to dig into water's two sneaky forms. Then, we'll introduce our heroes, the straw cutter and the door closer. After that, we'll have a little showdown to highlight the key differences. Then, we'll put it all together in the ultimate slab detail. You know, the one the ARE just loves to test. And if you stick around till the end, I've got the perfect cheat sheet for you to screenshot.
Okay, let's dive in. You know, it sounds almost too simple, but really, truly getting the difference between liquid water and water vapor, that's the key that unlocks everything else. Once this clicks, the rest is going to make so much more sense.
All right, let's bring in our first defender. To fight that visible enemy, that liquid water trying to soak right into our buildings, we need a really smart strategy. It's time to meet the straw cutter.
So what in the world is a capillary break? Well, think about it like this. Materials like concrete or brick, they're filled with all these teeny tiny microscopic pores. And liquid water uses these pores just like a straw, literally sucking itself up against gravity. That's called capillary action. A capillary break is just any detail we design to, well, cut that straw.
So how do we cut the straw? It's actually pretty straightforward. You just have to physically break that path. And there are two main ways to do it. First, you can create a gap that's just too big for the water to jump across. Think of an airspace in a wall, or a nice thick layer of gravel. Or, strategy two, you can stick a non-absorbent material in the way that just acts like a dead end.
Now, let's look at where you're actually going to see this on the exam, because I guarantee you these classic details are going to show up. You need to know them cold.
Okay, first up, right under a wood sill plate that's sitting on a concrete foundation, that little foam gasket, the sill sealer, that's the capillary break. It stops moisture from the concrete from wicking up and rotting the wood. Second, in a brick veneer wall, that air cavity behind the brick is the main capillary break. It stops rain that soaks the brick from getting any further. And third, that layer of clean gravel under a slab on grade, classic capillary break. It breaks the connection to the damp soil below.
So, we've handled the liquid, but what about that invisible enemy, the gas? Yeah, for that we need a whole different kind of defender. So let's meet our second hero, the door closer, also known as the vapor barrier.
Now, what's so wild here is that we're talking about a completely different physical process. A vapor barrier, or a vapor retarder, it doesn't cut a straw. It closes a door. It's designed to stop water vapor, that invisible gas, from moving through a material. And that movement is called diffusion. It's just nature trying to balance things out, moving moisture from a humid area to a drier one.
The strategy here is totally different. It's not about a gap. It's about putting up a material that's so dense, so non-porous, what we call impermeable, that those little gas molecules just can't get through. They hit a wall. Think of a plastic sheet, like 6mm poly, or the shiny foil on the face of rigid insulation. It's an airtight seal.
And this right here, this brings us to the most critical difference between these two. With the capillary break, the location is important, sure, but with the vapor barrier, the location is everything. I mean it. Getting this wrong can cause your building to fail in a really, really bad way.
And this is why it's so risky. If you put a vapor barrier on the wrong side of a wall for your specific climate, you can actually trap moisture inside the wall assembly. Then, when the temperature changes, that trapped vapor turns back into liquid water. It condenses, and that leads to mold, rot, and just a total disaster. You've literally turned the solution into the problem.
All right, it's time for the main event. Let's put these two head-to-head so we can really lock in the differences. This right here is the core of what you've got to know for the exam.
This table says it all. Just look at that first row. A capillary break fights liquid water. A vapor barrier fights a gas. That is the fundamental difference.
Everything else flows from that. A capillary break can breathe, meaning vapor can still pass through it. A vapor barrier, by definition, cannot. And check out that risk of error. It is way, way higher for a vapor barrier.
You know, if you remember just one single thing from our whole chat today, make it this sentence. A capillary break cuts the path that liquid water travels. A vapor barrier closes the door so that water vapor can't pass through. It's all about cutting a path versus closing a door.
And now for the RE plot twist. Because of course there's a plot twist. What happens when you're fighting both enemies in the exact same spot? What happens when one material has to do both jobs at the same time? Well, that's exactly what's going on under a concrete slab.
This is a concept that the RE absolutely loves to test. That simple sheet of plastic you see under a slab, it's a superhero doing two jobs. Because it's a solid, non-absorbent sheet, it physically cuts the straw for liquid groundwater. That makes it a capillary break. But because it's also impermeable to gas, it closes the door to water vapor, which makes it a vapor barrier. One material, two jobs.
So, let's build the perfect slab from the ground up, exactly how you should detail it. Okay, you start with your compacted soil. On top of that, a thick layer of clean gravel. That's for drainage, and it's our first capillary break. Next, your rigid insulation. And here's the absolute key. On top of the insulation, you put your poly sheet. That's your second capillary break and your vapor barrier. Then, you pour your concrete slab right on top of that.
Now this brings up the most common question I get about this detail, and it's one the ARE loves to ask. Why on earth does that plastic sheet go on top of the insulation instead of underneath it?
The answer is actually pretty simple. You always want to protect everything above the membrane. Putting it here keeps the insulation from getting waterlogged and losing its R value. More importantly, it keeps the concrete slab itself nice and dry, which is critical if you're ever going to put down sensitive flooring like wood or vinyl. It protects the entire assembly. This is the best practice detail you have to know.
Okay, let's bring it all home. Go ahead and get your phone ready to screenshot this next slide. This is everything we've covered, all boiled down into your final study notes.
And there it is. The capillary break fights liquid water by cutting the straw. The vapor barrier fights water vapor, a gas, by closing the door. And for that critical slab detail, remember that the membrane goes on top of the insulation to protect everything above it. If you can master these 3 points, you have totally mastered this topic.
So now you can see how just understanding the state of water, liquid versus vapor, is absolutely fundamental to designing good, durable buildings. You've learned how to see the invisible enemy. So the question I'll leave you with is, what other invisible forces, like air pressure or heat transfer, are shaping your designs right now? Keep asking those big questions, and we'll see you in the next one.